The silence came first, not the silence astronauts train for, not the familiar radio delay between Earth and deep space. This was different. Inside the spacecraft, every display still glowed. Every computer continued processing thousands of measurements every second. Life support systems hummed exactly as designed. Navigation remained stable. The crew followed their checklist without interruption. Yet outside the windows, something refused to fit decades of expectations. For nearly an hour, nobody on Earth could hear a single word. The moon itself stood between the spacecraft and every antenna on our planet, creating one of the oldest communication blackouts in human spaceflight. It was a moment mission planners had rehearsed for years. But rehearsing isolation and living through it are two very different things. Because during that silence, cameras continued recording, optical sensors remained active, navigation instruments kept measuring, radiation detectors sampled the invisible environment surrounding the spacecraft. Every system quietly collected evidence. No one at Mission Control could see any of it, not yet. When communications finally returned, engineers expected nothing more dramatic than routine telemetry confirming another successful milestone in humanity's return to deep space. Instead, they began downloading data unlike anything collected during previous lunar missions. Nothing suggested danger, nothing indicated equipment failure, yet several observations immediately demanded a second look, then a third, and eventually entire scientific teams began comparing the measurements against decades of lunar mission archives. The mystery wasn't that the spacecraft had encountered something supernatural. The mystery was far more interesting. Some of the observations simply didn't behave the way existing models predicted. To understand why that matters, we have to go back several years. Back to the mission that made those observations possible. On April 3, 2023, NASA announced the 4 astronauts selected for Artemis II: Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, mission specialist Jeremy Hansen of the Canadian Space Agency. It was more than another astronaut announcement. It represented a turning point in space exploration. For the first time since the Apollo era, humans would once again leave low Earth orbit. More than 50 years had passed since Apollo 17 lifted away from the lunar surface in December 1972. An entire generation had grown up without seeing astronauts travel into deep space. The Artemis program aimed to change that. But Artemis II was never designed as a landing mission. Its purpose was different, far more demanding in many ways. Every major system aboard NASA's Orion spacecraft would face its first complete human test beyond Earth's protective magnetic field. That meant propulsion, navigation, life support, communications, thermal control, power generation, radiation monitoring, emergency procedures, everything. Every component had to perform exactly as expected before astronauts could eventually attempt another lunar landing. The stakes were enormous. NASA had invested years of engineering effort across multiple centers, thousands of scientists, thousands more technicians, countless simulations, millions of lines of software code, and billions of dollars. Yet despite all that preparation, one simple reality remained impossible to eliminate. Deep space refuses to behave exactly like Earth. Even after decades of robotic exploration, humans have spent remarkably little time beyond low Earth orbit. The Apollo missions together accumulated only a tiny fraction of the experience modern engineers would ideally want. Every new mission, therefore, becomes more than transportation. It becomes research, continuous research. Every minute, every kilometer, every sensor reading matters, especially around the moon. Because although the moon appears familiar in our night sky, it still holds countless unanswered scientific questions. Its far side remained completely unknown until the Soviet Lunar 3 spacecraft photographed it in 1959. Those blurry black and white images transformed astronomy overnight. The hemisphere permanently facing away from Earth looked nothing like the side humanity had observed for thousands of years. The near side contains broad, dark volcanic plains known as Maria. The far side does not. Instead, it is dominated by ancient highlands, towering crater walls, thicker crust, different chemistry, different geological history. Even today, scientists continue debating exactly why the two hemispheres evolved so differently. Some theories point toward uneven internal heating billions of years ago. Others suggest massive impacts altered crust formation during the moon's earliest history. No single explanation answers every question. That alone makes every modern lunar mission scientifically valuable. But geology is only part of the story. The far side also offers something Earth can never provide: silence, radio silence. Earth constantly floods nearby space with artificial radio signals, television broadcasts, radar systems, military communications, cellular networks, satellite transmissions. The planet glows with electromagnetic noise. The moon blocks all of it. Its far side becomes one of the quietest radio environments anywhere in the inner solar system. That extraordinary silence has fascinated astronomers for decades. Future observatories could one day search for faint signals from the earliest universe without Earth's constant interference. Some scientists even describe the lunar far side as the most valuable location for radio astronomy near our planet. But achieving that vision requires understanding the environment first. How stable is it? How much radiation reaches the surface? How does lunar dust behave? How do charged particles interact with the terrain? These questions are not merely academic. Future astronauts may live there. Future telescopes may operate there for decades. Every measurement collected today shapes missions that have not yet launched. That is why Artemis II carries significance beyond its own objectives. Its observations become the foundation for everything that follows, including Artemis III, future lunar habitats, surface power systems, scientific laboratories, eventually, perhaps even permanent settlements. But before any of that becomes reality, engineers must answer one fundamental question. What is it actually like to travel through deep space with humans on board? No simulator on Earth can perfectly reproduce the environment between Earth and the Moon. Vacuum can be recreated, temperature extremes can be approximated, radiation can be modeled, computer simulations can predict thousands of scenarios. Yet predictions remain predictions. Real missions produce real evidence, sometimes confirming expectations, sometimes challenging them. History repeatedly shows that exploration rarely unfolds exactly as planned. Apollo astronauts encountered unexpected lunar dust behavior. Space shuttle crews observed atmospheric phenomena invisible from Earth. The International Space Station continues producing discoveries about long-duration human physiology that no laboratory anticipated. Space has a habit of surprising us, not through science fiction, through reality, and reality is often far stranger. As Artemis II prepared for its historic journey, scientists understood that unexpected observations were almost guaranteed. The question was never whether surprises would appear. The question was what kind. Would they involve radiation, navigation, human physiology, the spacecraft itself, or something hidden within the data that nobody thought to search for until after the mission ended? That possibility has become increasingly important in modern exploration. Today's spacecraft generates staggering amounts of information: high-resolution imagery, spectral analysis, star tracker measurements, thermal readings, particle counts, magnetic field observations, navigation solutions, system diagnostics, environmental monitoring. Each second produces more data than entire missions generated decades ago. Hidden within those enormous data sets can be tiny anomalies, not necessarily extraordinary, not necessarily alarming, simply unexpected. Sometimes those anomalies disappear after calibration, sometimes they reveal instrument limitations, and sometimes they open entirely new scientific investigations. That possibility is exactly what makes Artemis II far more than another trip around the Moon. Because somewhere during humanity's return to deep space, while Earth disappeared behind a wall of ancient rock, the spacecraft continued watching, recording, measuring, collecting evidence that nobody on Earth could see until the silence finally ended. And once that data reached scientists, one particular sequence of observations began raising questions that reached far beyond a single mission. Those questions would eventually lead researchers back to one of the least understood environments anywhere within reach of human exploration: the dark side of the Moon, where the absence of radio signals does not mean the absence of discovery, and where some of the most important findings are not the ones astronauts notice immediately, but the ones scientists uncover long after the spacecraft has already returned home. When researchers finally began examining the complete stream of Artemis II data, they did not start by looking for mysteries. They looked for mistakes. That is standard practice after every major space mission. Before any scientific conclusion is accepted, engineers first assume the spacecraft, not nature, is responsible. A sensor may have drifted, a camera could have overheated, a software algorithm might have interpreted light incorrectly. Even a tiny vibration can influence precision instruments. Every possibility must be eliminated. Only then does an unusual observation become scientifically interesting. This cautious approach has shaped modern space exploration for decades. It is why discoveries announced by NASA often appear months, or even years, after the observations themselves. Verification comes before excitement. That philosophy became especially important around the Moon. Unlike Earth, the Moon possesses no global magnetic field capable of shielding its surroundings from the continuous stream of charged particles flowing outward from the Sun. Known as the solar wind, these particles travel at hundreds of kilometers per second. Most pass harmlessly through space. Some strike planetary atmospheres. Others collide directly with exposed surfaces. The Moon receives them almost constantly, for billions of years. Each impact changes the surface by microscopic amounts. Scientists call this process space weathering. Individual atoms are knocked free. Minerals slowly darken. Tiny glass particles form inside lunar soil. Over immense spans of time, the landscape itself evolves without wind, rivers, or rain. It is a geological process unlike anything on Earth. But the Moon's interaction with space becomes even more complicated. Every month, during part of its orbit, the Moon passes through Earth's magnetotail. This enormous extension of Earth's magnetic field stretches millions of kilometers away from the Sun. Inside that region, the lunar environment changes dramatically. Solar particles decrease. Different charged particles become dominant. Electrical conditions shift. Dust behavior may also change. Scientists are still investigating exactly how these transitions affect the lunar surface. That uncertainty makes every direct measurement valuable, especially measurements collected by humans traveling through the region. Artemis II was expected to provide some of the most detailed environmental observations ever gathered during a crewed lunar flyby. Radiation monitors continuously sampled energetic particles. Thermal sensors tracked changing temperatures across the spacecraft. Optical instruments recorded sunlight reflecting from the lunar surface. Navigation cameras observed stars with extraordinary precision. None of these systems existed simply for beautiful pictures. Every one served scientific and engineering purposes. Together, they created an extraordinarily detailed portrait of the environment surrounding Orion, yet one of the most challenging environments remained almost invisible: lunar dust. During Apollo, astronauts quickly discovered that lunar dust behaved unlike ordinary sand. It clung stubbornly to spacesuits, worked its way into seals, scratched delicate surfaces, entered the cabin despite careful cleaning. Some astronauts even reported irritation after breathing small amounts carried inside on their equipment. At first glance, lunar dust appears harmless. Under a microscope, it tells another story. Unlike grains shaped by water or wind on Earth, lunar particles remain sharp, jagged, angular. Billions of years without erosion leave them resembling microscopic shards of broken glass. That shape allows them to stick almost everywhere. Electrostatic charging makes the problem even worse. Sunlight can cause dust particles to gain electrical charge. As conditions change between sunlight and darkness, those charges change as well. Some researchers believe this process occasionally allows tiny grains to lift slightly above the surface before settling again. The idea remains under investigation. But if confirmed, it would affect everything from future lunar vehicles to solar panels and scientific instruments. Understanding dust is therefore not a minor engineering concern. It is essential for long-term human exploration. Imagine trying to build a permanent base where every exposed surface gradually accumulates electrically charged abrasive powder. Airlocks, rovers, solar arrays, optical lenses, mechanical joints. Every system would eventually confront the same challenge. That is why Artemis missions are gathering environmental data long before permanent habitats exist. The goal is preparation, not reaction. Meanwhile, another mystery has quietly occupied lunar scientists for decades: transient lunar phenomena, often abbreviated as TLP. The reports stretch back centuries. Observers occasionally described brief flashes, localized glows, momentary color changes, small bright patches appearing and disappearing across the moon's surface. Most reports lasted only seconds or minutes. Many occurred before photography became common. Naturally, skepticism followed. Human eyesight is imperfect. Earth's atmosphere distorts incoming light. Telescopes introduce optical effects. Expectation itself can influence perception. For years, many astronomers suspected that most historical reports resulted from observational errors rather than genuine lunar events. Yet the mystery never disappeared completely. Modern spacecraft have occasionally recorded subtle changes consistent with some historical descriptions. Not dramatic, not supernatural, but enough to keep scientists interested. Several explanations remain possible. Tiny meteorite impacts constantly strike the moon. Fresh impacts briefly expose brighter material. Electrostatic dust movement may slightly alter surface reflectivity. Rare releases of trapped gases beneath the crust have also been proposed, although evidence remains limited. No single explanation accounts for every historical observation. That uncertainty continues to motivate research today. Artemis missions are expected to improve understanding by providing better cameras, better sensors, and more continuous observations than Apollo could ever achieve. Technology has transformed dramatically since the 1970s. Modern imaging systems detect details Apollo astronauts never had the ability to record. Artificial intelligence now assists in comparing enormous image libraries. Machine learning algorithms identify tiny differences across millions of pixels that human observers could easily overlook. Instead of searching manually through thousands of photographs, scientists allow computers to highlight unusual changes automatically. Only afterward do researchers investigate whether those changes represent genuine discoveries or merely instrument artifacts. The process is meticulous, slow, deliberately skeptical, exactly as science should be. Then there is the far side itself. For generations, people called it the dark side of the moon. Technically, the phrase is misleading. The far side receives just as much sunlight as the near side. Half of it experiences daylight, while the opposite half remains in darkness, exactly like every other rotating world. The real difference is communication. When Orion passes behind the moon, radio contact with Earth disappears. No live conversations, no real-time telemetry, no instant troubleshooting. For those minutes, the crew becomes entirely self-reliant. Mission control cannot intervene. Engineers cannot offer immediate advice. Every decision rests with the astronauts and the spacecraft's onboard systems. It is one of the few moments in modern exploration where deep space crews experience genuine operational independence. That isolation carries psychological significance as well. Low Earth orbit always keeps astronauts relatively close to Earth. The moon changes that perspective completely. As Orion loops around the far side, Earth vanishes, not beneath the horizon. It disappears entirely. Nothing blue remains outside the windows, only gray terrain, black space, countless stars. Apollo astronauts often described this experience as profoundly humbling. Several later said it permanently changed how they viewed humanity. There were no borders, no nations, no visible conflicts, only one distant world suspended in darkness. Artemis II would give another generation the same view. But unlike Apollo, today's spacecraft carry vastly more sophisticated scientific instruments. Every second of that journey contributes to future missions, future habitats, future observatories, future explorers, and possibly one day, future generations born beyond Earth. That larger vision explains why seemingly ordinary measurements matter so much. A slight variation in radiation, an unexpected thermal fluctuation, a change in reflected sunlight. Individually, such observations may appear insignificant. Together, they reveal how the lunar environment truly behaves, sometimes confirming decades of theoretical work, sometimes exposing assumptions that require revision. Because exploration has never been about proving ourselves right. It has always been about discovering where we were wrong. And as Artemis II approached the moment when the moon would finally block every radio signal reaching Earth, one particular sequence of environmental measurements began unfolding in complete silence. No engineer could watch it happen live. No scientist could analyze it in real time. The spacecraft simply continued collecting data, second after second, while hidden behind the ancient highlands of the moon. Only later, after communications returned, would researchers realize that those measurements deserved a far closer look. And the explanation would lead them into one of the least understood interactions between the sun, the moon, and the invisible forces that fill the space between worlds. When Orion finally emerged from behind the moon, the silence ended in an instant. Signals raced across nearly 384,000 kilometers of space. Mission Control began receiving thousands of packets every second. Telemetry, engineering logs, navigation updates, environmental measurements, camera imagery. Everything the spacecraft had recorded during the communications blackout started flowing back to Earth. For the astronauts, it marked another successful milestone. For the engineers, however, the real work was only beginning. Every byte of information had to be verified. Every sensor reading had to be compared against prediction models. Every photograph had to be cataloged. This process isn't glamorous, but it is where many of the most important discoveries in space exploration actually begin. Not during the mission, after it, because data often reveals patterns that nobody notices in real time. Modern missions generate enormous amounts of information. A single high-resolution camera can produce thousands of images. Navigation systems constantly calculate the spacecraft's position using distant stars. Radiation detectors count energetic particles every fraction of a second. Thermal sensors monitor temperatures across dozens of locations. Accelerometers measure tiny vibrations almost impossible for humans to feel. Each system tells only part of the story. Together, they create an extraordinarily detailed picture of everything happening around the spacecraft. Scientists call this multi-instrument analysis. If one instrument records an unusual event, researchers immediately ask a simple question. Did any other instrument observe something at the same moment? If the answer is no, the anomaly may simply be sensor noise. If the answer is yes, the investigation becomes much more interesting. This method has transformed planetary science. Instead of trusting a single measurement, researchers compare independent observations collected by completely different systems. Agreement increases confidence. Disagreement raises questions. That philosophy has helped validate discoveries across the solar system. It confirmed water ice inside permanently shadowed lunar craters. It strengthened evidence for ancient rivers on Mars. It revealed unexpected activity on icy moons orbiting Jupiter and Saturn. Every major discovery begins with careful comparison, never assumptions. Meanwhile, another factor demanded close attention during Artemis II, cosmic radiation. On Earth, most people rarely think about it. Our atmosphere absorbs much of the radiation arriving from space. Earth's magnetic field deflects many charged particles before they ever reach the surface. Together, these natural shields protect life remarkably well. Beyond low Earth orbit, those protections largely disappear. Astronauts entering deep space experience an environment fundamentally different from anything aboard the International Space Station. High-energy particles arrive from multiple directions. Some originate from the Sun. Others were accelerated by distant supernova explosions thousands or even millions of years ago. Known as galactic cosmic rays, these particles travel through the galaxy at extraordinary speeds. Some carry enough energy to penetrate spacecraft walls. Others pass directly through human tissue. Most cause no immediate symptoms. But over long periods, cumulative exposure increases health risks. Understanding exactly how much radiation astronauts receive is therefore essential, especially for future missions lasting months or years. NASA has spent decades developing increasingly sophisticated radiation detectors. These instruments do more than count particles. They identify particle types, measure energies, track arrival directions, record changes over time. Each measurement helps scientists improve protective shielding for future spacecraft. Artemis II represents another critical step in that research, because eventually, NASA hopes to send astronauts much farther than the Moon, Mars. The journey alone could require roughly 7 months. Some mission designs estimate even longer travel times depending on planetary alignment. A complete expedition, including surface operations and the return trip, could approach 3 years. No human has ever attempted such a mission. Radiation remains one of its greatest engineering challenges. Every Artemis flight therefore contributes directly to humanity's long-term future in deep space. Yet radiation isn't always dangerous. Sometimes it becomes a scientific tool. For example, when energetic particles strike spacecraft materials, they occasionally produce secondary particles. These interactions help engineers understand how different shielding materials behave under real conditions. Computer simulations predict these effects. Real missions confirm them, sometimes revealing subtle differences that improve future spacecraft design. This constant cycle, prediction, observation, refinement, is how exploration advances, not through dramatic breakthroughs, through relentless improvement. Then there are the cameras. Most people imagine astronauts taking photographs simply to inspire the public. Beautiful Earthrises, crater landscapes, the blackness of space. Those images certainly matter. But onboard cameras perform far more practical functions. Star trackers identify spacecraft orientation by comparing observed star fields with enormous digital catalogs. Optical navigation cameras monitor the moon's position against background stars. Docking systems rely on precise imaging. Even surface reflections can help estimate spacecraft attitude. A single photograph often serves multiple engineering purposes simultaneously. Sometimes, unexpected science appears in the background. This has happened before. The Hubble Space Telescope was built to study distant galaxies. Instead, it also transformed our understanding of planetary atmospheres, comet impacts, and the expansion of the universe. The Cassini mission to Saturn unexpectedly revealed towering water plumes erupting from Enceladus. The New Horizons spacecraft discovered astonishing geological complexity on Pluto despite flying past for only a few hours. Again and again, space missions find more than they originally expected, not because engineers overlooked something, because nature is more complicated than our models. The moon continues proving that lesson, even after centuries of telescopic observation, even after robotic orbiters, even after 12 Apollo astronauts walked across its surface. Questions remain. One concerns magnetic anomalies. Although the moon lacks a global magnetic field, certain regions possess surprisingly strong localized magnetism. These magnetic patches were first detected decades ago. Scientists believe they formed billions of years ago, possibly preserving remnants of an ancient lunar magnetic dynamo or resulting from massive asteroid impacts. Exactly how they formed remains debated. These localized magnetic regions interact differently with the solar wind than surrounding terrain. Some appear to partially deflect incoming charged particles. Others influence the movement of electrically charged dust. One particularly famous example is Reiner Gamma, a bright swirling pattern visible from Earth through moderate telescopes. Unlike ordinary lunar features, it is not associated with an impact crater. Instead, it coincides with an unusually strong magnetic anomaly. Its distinctive swirling appearance has puzzled researchers for decades. Several theories suggest that localized magnetic fields protect certain areas from space weathering. If true, surrounding regions darken over billions of years while protected areas remain brighter. The result is an enormous natural pattern stretching across the lunar surface. Future Artemis missions may help answer whether this explanation is complete or whether additional processes are involved. Understanding these magnetic regions matters for another reason. Future astronauts may eventually operate equipment near them. If localized magnetic environments influence dust behavior or radiation exposure, engineers need to know before constructing permanent facilities. Every unanswered scientific question eventually becomes an engineering question, and every engineering question affects human safety. That is why Artemis is not simply repeating Apollo, it is building an entirely new foundation. Apollo proved humans could reach the moon. Artemis must prove humans can remain there. That requires far more knowledge, far more precision, far more patience. As scientists continued reviewing Orion's measurements, they began comparing the mission's observations against data collected by previous spacecraft. The Lunar Reconnaissance Orbiter, the Artemis probes, the Kaguya mission from Japan, India's Chandrayaan spacecraft, China's growing series of Chang'e lunar missions. Together, these missions have produced one of the richest scientific archives ever assembled for a planetary body, yet no archive is ever complete. Each new mission fills gaps left by those before it, sometimes confirming decades-old conclusions, sometimes forcing researchers to reconsider them. That is precisely what makes exploration so compelling. The frontier never disappears. It simply becomes more detailed. And somewhere within Orion's vast collection of environmental data, researchers noticed that one sequence of measurements aligned in a way that demanded much closer investigation. Individually, each observation appeared ordinary. Collectively, they hinted that the invisible environment surrounding the moon might be behaving in ways scientists still do not fully understand. The evidence was subtle, the interpretation remained cautious, but the questions it raised would eventually connect Artemis II to decades of unfinished lunar research and to one of the oldest mysteries surrounding Earth's nearest neighbor.